Recall what we talked about in class when we first started to cover this idea of center of mass. We had the example of somebody's classes and their grades, along with the grade points that go with those grades. And what we talked about was the more units or the more credits a class is worth, the more it'll affect your GPA. So this chemistry and this calculus class, because they're more credits, they're going to affect the grade point average more. And the calculation was done by multiplying each of the grade points with the corresponding weights, in other words, the units or the credits. And that's an example of what's called a weighted average. When you divide by the sum of the weights, which is right here. So we're going to use that idea to talk about center of mass, which is the topic we were trying to build up to. Okay. When you did activity 6.3.3, one of the things that you should have been able to visualize by the end of the activity is that you have this balancing point that you're looking for, and we're assuming everything is a point mass. In other words, it's a line, a single axis, and we have these points on it that have a mass. M1, M2, M3, and these have locations on this axis, X1, X2, and X3. So since we're in a one-dimensional situation, we have that the center of mass, if you just have point masses, kind of like this picture, you're going to have that the center of mass is a weighted average, very similar to when we were talking about GPA. So we're going to use this formula to help us figure out what if we're thinking about something like a bar, a continuous bar where we have that the density is distributed throughout this thin bar. So we're thinking of, even though this is technically a three-dimensional object, we're really thinking of it as if it's a one-dimensional object. Okay. Remember that we mentioned density doesn't have to be constant. It doesn't have to be uniformly dense throughout the object. We were talking about soup in class last time. Part of the soup is more liquid than other parts. Some parts are more solid than others. So the density of the soup is not uniform throughout the soup. But if we had a function that tells us at any given point what the density is, that's going to be what allows us to compute a weighted average. Very similar to what we had when we just had point masses, like in activity 6.3.3. Remember that mass, when we first talked about it, was equal to density times volume. But because we're in a one-dimensional situation, we have that, so in a one-dimensional situation, there is no volume, there is no area, so mass is actually equal to, let me erase this 3D object since we're not thinking of 3D objects. Mass in this case is going to be equal to density times length. Okay. That's why if we just had a single slice of thickness delta x at a certain location, xi, the mass of that slice would be calculated by taking rho of xi times delta x. We're going to construct a Riemann sum and let the pieces get infinitely short and have infinitely many pieces, which is the usual construction involving a Riemann sum. So working toward that, first we're going to give a name to this center of mass, this balancing point that we're looking for. It's called x bar. And if you look, it's very similar to this weighted average formula that we have up here. We're assuming we've cut the bar into n pieces and we have an approximation of its center of mass. Because again, we don't know how the density is distributed throughout the object. It's the function that tells us that. So by taking these slices, we have an approximation of the center of mass. If we rewrite this using sigma notation, we have something that looks like it's getting closer to being a Riemann sum. Notice there's a Riemann sum on the top of the fraction and another Riemann sum at the bottom. Because remember, we had to divide by the sum of the weights. And remember, each of these m's was obtained by rho evaluated at xi, for some I, times delta x. That's the mass of each slice of this bar. When we take that sigma notation and increase the number of slices indefinitely, we're letting n go to infinity. And so that turns into an integral, as we've seen when we first learned about integrals in Calc 1. So the center of mass, if we have a continuous function that's giving us the distribution of the density throughout the object, where the density is called rho of x. Remember, this is the Greek letter rho. It looks like kind of like a more rounded p, but it's actually rho, which is the Greek letter that corresponds to r. Along the axis from a to b, we have the integral from a to b of x rho of x dx. Again, that's the integral version of the Riemann sum up here in the numerator, divided by the integral from a to b of rho of x dx, which will give us the total mass of the object in this case.